We're going to finish off this unit on astrophysics by looking at the very, very beginning and the very, very end. Our primary topic to begin with here is the Big Bang. And you've probably heard of the Big Bang before, whether it's some understanding of the science behind the Big Bang, or the Big Bang as it shows up in pop culture. Maybe you've seen the movie The Theory of Everything, or you've watched the TV show The Big Bang Theory. The Big Bang is a really, really important origin story for our universe, and understanding um, kind of our general idea of what this means really results in understanding a deeper understanding of the universe itself. So we're going to go through really quick here the different stages in the Big Bang, because they all happen really, really fast, and there's some really important pieces in here that you should be aware of. So the Big Bang starts with a period known as inflation. And inflation is basically all of the mass in our universe started out as a lot of energy. E equals mc squared. Mass and energy are two forms of the same thing. And that energy gets converted into mass, expanding outward. Now, there isn't one solid theory of what it's expanding into. I know that's probably a question you have. Okay, like if our universe is expanding, like what's on the other side of that part of the bubble? We'll get to that in a little bit. But right now, the answer is nothing. As far as we know, there's nothing there. Now, inflation happens very, very quickly, expanding out in all directions, and eventually that energy gets converted into mass in the form of quarks. We're still at a tiny, tiny fraction of a second when the first quarks start to appear. Now, we have talked about quarks in this class as being the building blocks of matter, basically. So our subatomic particles that we're normally thinking of in chemistry class being protons and neutrons, they are both under the category of baryons, and they are made up of 3 quarks each. So eventually those quarks start to combine, and they form protons and neutrons, leading to this period of the natural laws starting to happen. So this is where our fundamental forces kind of come into being, that the matter is there to start interacting in different ways. And then once those natural laws are in place, this is when the quarks start forming into hadrons, leptons appear, and again, this is basically the beginning of protons and neutrons. Now, there aren't really elements yet. There's not really atoms. They're just these building blocks. The quarks being built into hadrons and leptons. Now, then at about 1 second, so all of this is within the first second of our universe. After about 1 second, now the simplest atoms start to form. Simplest atom is a hydrogen atom that is 1 proton and 1 electron. Sometimes there's a neutron in there as well. But simplest atom, 1 proton, 1 electron start to form in the nucleosynthesis era. Then we reach at about 200 seconds or so we're still in the span of minutes, something known as the opaque era. Now, something that I think is fascinating about the Big Bang, kind of this early universe, is you couldn't see through it. And there's a couple of reasons for that. One is it's so hot that it's actually glowing. So the color of our universe was more of an orange color at this stage in its life. And the high energy of the electrons meant that the electromagnetic waves couldn't actually travel through space. They were always being absorbed by these electrons and these atoms. So you couldn't have light travel through space, which meant you couldn't really see anything, because there was nothing to see, and there was no way that light could travel through. So it's known as the opaque era. Now, that lasted for a long time. The universe today, like, light wasn't able to really escape until about 300,000 years after that Big Bang. So I know it's kind of comical to see these different stages in seconds, and then like a little thing happened, and 300,000 years later, the universe. We're going to talk a little bit more about that moment here in a little bit, because we actually have evidence of that moment that light was then able to travel beyond. So you should have watched a little bit ago a movie talking about some of the different types of evidence that we have for the Big Bang Theory being accepted. Because for a long time it wasn't. It was actually a pretty controversial theory. And it's a hard thing to prove because it's a hard thing to measure, something that happened 13.8 billion years ago, as far as we know. And the evidence that was gathered, the strongest evidence that supported this theory, was actually kind of found by accident. And it's one of my favorite stories in science. And it's from these two scientists, Penzias and Wilson. And they were both scientists for Bell Labs. And they were actually doing some research on radio waves. And they were working on this new piece of equipment to measure radio waves as they were bouncing in different ways. And to get the measurements that they needed, they had to really lower the noise of their instrumentation, because all instrumentation has some base level of noise to it. And if you want really, really fine, detailed measurements, you need to decrease that noise. And they were doing their measurements, and they were seeing a lot of noise still. And they figured that they just hadn't tuned their instrument correctly. They found some pigeons that were roosting inside, so they were pretty sure, actually, for a while, that it was the pigeons and the pigeon poop that was causing the noise in this, that it was sensitive enough for that. So they cleaned all of that out, wiped it all down, reconfigured things, and they were still seeing the same noise. And what was interesting about this is it wasn't from anything man-made, because they could point it anywhere in the night sky, and they were still seeing this base level, and it was the same no matter where they pointed it. And the noise that they were seeing, when you map it out, looks something like this. This is actually a 360-degree view, all kind of crammed into one oval. And this picture here is a very, very famous picture. This picture is known as the CMB, the Cosmic Microwave Background. Microwave, in this case, just indicating the wavelength at which this noise is being broadcast at. So it's in the microwave part of the electromagnetic spectrum. Again, if you don't remember, microwave is somewhere in between infrared light and radio waves. So it's a pretty high, pretty long wavelength, low frequency form of electromagnetic light. Now, this cosmic microwave background radiation is really, really important in our discussion of the universe, because it is our best evidence that the Big Bang Theory is actually something that happened. And this microwave background radiation isn't actually from the moment of the Big Bang. It is from the moment that the universe was no longer opaque. So once light was able to travel outward, it's from that moment in time. And we see it coming outward. Basically, if you look up at the night sky, when you look at farther and farther stars, it's essentially like you're looking back in time, because the farther stars are away from you, the longer it takes light to get there. And there are stars that are actually billions of light years away. Now, billions of light years away, that actually makes it that the light that was emitted is actually pretty close to the moment that the universe was originally created. Now, this cosmic microwave background radiation is the oldest light that we can see. It is at the fringes of our observable universe. So looking at this is like looking back in time towards the very, very beginning of our universe. Now, why this actually made such a great form of evidence is related to some science that we've already talked about. Now, if we were to plot this out, this isn't actually just one wavelength. There is a spread of wavelengths that are here. Just like if you were to measure your toaster, the little coils in your toaster when they heat up, there is not just one wavelength. There's a spectrum of wavelengths that are presented. But there is a peak wavelength. And you should remember a relationship that we've talked about for peak wavelength. If we know that, and in this case, cosmic microwave background radiation is about 1 millimeter for its peak wavelength, we can calculate the temperature of our universe. Now, if I plug that in, 1 millimeter, 0.001 meters, into this 1 wavelength temperature relationship that we've used in the past, we can get that, oh, sorry, here's the max wavelength. We can get that the temperature of our universe is something around 2.9 or 3 degrees Kelvin. Now, the reason that this matters is that is what was predicted, knowing the rough estimate of the age of our universe. As the universe expands, the wavelength of light from that moment in time has expanded with it. And basically, if you think of drawing like a little wavelength on a rubber band and stretching that rubber band, the farther you pull it, the longer that wavelength is going to be. The calculations based on Hubble's law saying that there's about 13.8 or 14 billion years, how old our universe is, that predicts that by this time, the wavelength of that light should be about 1 millimeter. And what was interesting here is this was predicted before Penzias and Wilson found their measurement. And they weren't actually scientists that were looking for this theory. It was them publishing a paper about this noise that they saw that ended up crossing paths with the scientists that were looking actively for this background microwave radiation. And it is those two pieces that came together that ultimately led to the discovery of this CMB and the proof of the Big Bang theory. So now that we've had an opportunity to talk about the origin story of our universe, let's talk about what is to come. So if we know that the universe originated in some tiny infinitesimally small point in space, and it's expanding outward, how does it end? Does it keep expanding forever? Does it come back down to that point? And all of these have been a variety of different theories throughout time and have been debated by some of the best scientists. Einstein is actually a key player here in this discussion. Go figure, he's everywhere. So there are a few different theories that were out there talking about what's next. The first theory is that the universe is static and infinite. This is actually the theory that Einstein prescribed to. That his theory of the universe was that it is what it is. It's not changing. It's not getting bigger. It's not getting smaller. It's just everywhere. It's all places, static and infinite. He was actually so confident in this theory that as he was doing some equations for one of his other primary theories, he included a little fudge factor because his theory didn't predict a static universe, like the math didn't. So he knew that the universe was constant, so he added a little constant to it that made it so it would work, that the math would result in what he believed. Number two is that the universe is expanding and slowing to a stop, that inside the universe is a lot of mass, and mass has gravity. So as things are expanding, sure, it's getting bigger, but the mass is also pulling everything back in, kind of creating it, like bringing it to a halt. So that at some point, the universe will reach its maximum size and then stop there, find its equilibrium. Number three is kind of related to that. The fact that the universe has mass, and as it gets bigger, it's slowing down, but then eventually it wouldn't stop because there is gravity inside, so it's actually going to pull back inward, then speed up more and more and more, and then crunch back in a theory that's known as the Big Crunch. So kind of the opposite of the Big Bang, and then end in a point just like it began. And then the last is that it is expanding and it's accelerating. And this is actually fairly new science that not too many years ago, I think it was like 5 or 6 or 7 years ago, the Big Bang or the Nobel Prize was awarded to some scientists that proved for the first time that not only is it expanding, it's accelerating. That the light that's being emitted from farther and farther away galaxies are not a linear relationship anymore, like Hubble's law would necessarily expect, that the farther and farther measurements you take, the faster and faster they're going, which means that it's not constant at all. Turns out Einstein's fudge factor can prove this. So he was right even when he was wrong. Pretty fascinating, dude.